So we are covering the second textbook on ocean engineering first. And this chapter is about chapter 8 of Underwater Acoustics. And sound and acoustics, and sonorification, speed of sound and sound propagation, and the application area. So this one shows a decibel scale. And this looks like 0 to 140 something. You may know that the scale is made of a log scale, exponential scale. There is a complicated calculation equation. But anyway, this is what we heard about the scale on decibel. And what is sound and acoustics and difference? Sound is a wave or mechanical wave, not electronic or light. Sound is mechanical wave. That is an oscillation of pressure transmitted through a medium like a solid, liquid, gas. Usually we are hearing sound through the air. So air is the medium, but we can also listen through the water, also through the steel pipe, solid, so which is detected by a receiver as a change in pressure. Acoustics is a science that deals with the sound of production, control, transmission, and reception and effect of sound. All right, and then there is another image of a decibel scale. So you see that there is about 140 to and 0. It's the usual scale we are basing in the nature or social surrounding. So you see that louder sound coming from human body can also reach very high decibel level. Underwater acoustics. This is the main area we are interested in. So the first is said by Leonardo da Vinci in 15th century. So long time ago already he knows about underwater acoustics or interested in. If you cause your ship to stop, the ship is stopping, and then place head of a long tube in the water and place the outer your ear carefully. Hear ships, and you can hear ships at a greater distance from you. Comparing to the air, you can hear more on inside water. That is interesting portion of. Okay. And so that we can apply this phenomena or property of sound on the water. We use a sonar system. Sonar is a short name of sound navigation and ranging. And then underwater communication is done using sound. And then also underwater localization and navigation. Localization means finding your position or other object too. So position finding is we call it localization, and navigation based on this localization. So robot usually doing a same way, localization and navigation. In seismic exploration, we try to find out the oil and gas reservoir through using sound seismic exploration. Right. So this is a picture coming from seismic exploration. You see that the survey ship has a source of shock waves based on air gun, and they have a long line of hydrophones, receivers. And there's a seabed at the first line. So under the seabed, there is layers of earth or stones and soils and pebbles. So there is a sedimentary rock layer has so the sound is going sometimes deeper, and then reflected wave is coming back, and sometimes there can be a oil reservoir, water, and porous reservoir rock or gas. So by analyzing, turning back of sound, you can figure out what is inside. It is very similar to if you go to a medical hospital, they use ultrasound scanning, especially for baby inside our lady. So you can see the outline of the baby inside the belly. So that also use sound waves returning back. So similarly, we can get the image of the seabed pictures. But the quality and accuracy may be lower than the medical ultrasound because of the size and because of other reasons. But anyway, it can be a help. Sonar, how does sonar work? Sonar use sound echoes to locate object localization, as does radar. So radar is doing similar, but the emission of radar is electromagnetic wave rather than sound. So the theory or fundamental principle is very similar. So at the bottom, you see that original wave is generated sender, speaker, or receiver. And there is an object. So the object has a reflected wave is coming, so that can figure out. And that fundamental theory is very similar to that of bat, dolphin, so that the submarine is trying to um, learn how the bat and dolphin is finding out object. Why we use sonar rather than radar in underwater? Because radar should be a better technology. Because the electromagnetic wave which is used by radar is a propagation loss or attenuation. The seawater is very large, prohibitively large, so we cannot use it. So this picture shows some attenuation absorption spectrum or attenuation coefficient based on wavelengths of liquid water, red color, and ice, blue line, similar. And then green one is water vapor. So still water is inside the vapor, still has bigger attenuation than pure air. Right? Then communication. So once again, there are three types of carrier waves. One is electromagnetic, optical wave, and acoustic wave. That is common to any communication. A special. Really? Do you have any question? No? But underwater, we usually use acoustic wave rather than electromagnetic and optical. So this is a picture, which the frigate trying to find out where is the submarine, enemy submarine. So there is a sound source, ping, ping sound is usually, you remember from the film. And then there is a hydrophone array of a long array so that the returning back waves are sensing so that we can localize, finding out submarine, enemy submarine. And electromagnetic wave communication can be at higher frequency and bandwidth. This you can imagine using the smartphone. And as smartphone has developing and 4G and 5G, we are using 5G, and in the future it can be a 6G. They are saying that commercial saying that uh, gigabyte transfer of data so that you can download films of 1 hour, 2 hour instantly to your smartphone. So that is a higher frequency gigahertz or megahertz, and then the bandwidth is bigger. So it's good. But the limitation is due to observation or attenuation in what? Of electromagnetic. So we cannot use in normal situation. So very large antenna can be used together, but this is not cost effective. Also, you cannot carry the big antenna with you. That is another problem. Optical wave is similar to electromagnetic wave. Also offers available high data rate transmission, but same as the observation attenuation is very large, so that, and also optical wave has a scattering effect. It is not good on those. And this table shows the speed of sound in different material. Usually we know that air, it is sound speed is 330 meter per second. Right? But on the water, inside water, it is about how many times? 3 times more than 3 times faster. The sound speed is 3 times faster. And then the metal like gold or steel, aluminum, uh, their speed is even higher. So for the aluminum, you say can be 20 times higher than speed inside air. Is interesting property so that you can use or property for fish. Acoustic wave is the most preferred signal used as carrier by application inside water, underwater. Because of the low absorption, even though the data transmission is slower compared to the other carrier signals such as electromagnetic, the data amount speed is low, but the low absorption characteristic is the reason why we choose acoustic signal travel at longer range. So the electromagnetic wave can be used for short distance, only short distance. An active sonar employs a transmitter, so, and there is a passive sonar and active sonar. The active sonar is they generate, send out sound pulses, and then receiver to record returning echoes. But passive sonar does not generate sound, but they just listening. So that is why, because if you generate sound that can be detected by enemy first, so you can it is not easy. It is you don't want to generate noise to make enemy find out first. So when you see, remember the film from Second World War, there is a many good film between a battle between German submarine and uh, United States or UK frigate or battleship. But once they are engaged, they try to be quiet. There is a sound spreading property. The left one shows a speaker spreading because there is a point source of sound. You can imagine that this is very similar to light, a light source, single light source. The spreading out of light and sound is same as spherical shape. But when right hand side upper, there is a line source of sound or line source of light, such as line light headlamp in the house. The spreading shape can be cylindrical spreading, and depending on the distance, the intensity can be lowered down. And in ocean, sound sources and noise, several kind. One is machinery noise and flow noise and fouling. And another important one is noise coming from propeller cavitation. So this picture shows cavitation, generated cavitation from the propeller. And then ambient noise. Ambient noise is noise coming from surrounds. Something like a hydrodynamic noise, seismic, ocean traffic from other ships, and biological noise, say coming from dolphin something. And this one shows a chart of a vertical one shows a spectrum level of decibel. So noise is bigger and higher one. And then right hand side, the horizontal axis is a frequency. And you see that at the left top, there is an earthquake. And then biologies and what is it? Precipitation. And then fourth one is ships, industrial activity, and then sea ice also generate sound. And what else? Okay, and there is a video. See if we can find this right. Oh, there's more. All right, that's good. Sorry, I did not check sound. Share that one.
You're diving in the ocean when suddenly a large military submarine sails next to you. Question: how can this vehicle harm you? Well, the possibilities are endless, but the one way you probably didn't think of was sonar. Sonar is an acronym that stands for Sound Navigation and Ranging, and as the name suggests, is used for navigating and ranging objects underwater. Sonar is used because sound waves travel through water much better than radar or light. Since submarines, especially military variants, typically do not have windows, sonar is a submerged submarine's eyes. There are two types of sonar, active and passive. Passive sonar simply listens to the sound of the water. It listens for marine life and other ships that may be nearby or using active sonar. Active sonar, on the other hand, actively sends out pulses of sound and listens for how long they take to return when they bounce off an object. Sonar works by calculating the echoes. Once you know the speed of sound in water and the time it takes for the signal to return, you can determine an object's distance. And this is a type of sonar that could potentially harm you if you were diving next to a submarine for some reason. So how can it harm you? Well, sonar is a sound, a very loud sound. A sonar ping can be as loud as 235 decibels. To put that into perspective, the loudest sound you can hear before your eardrums rip apart is about 160 decibels. Above 194 decibels, sound waves become classified as shock waves in the air. In water, however, sound can get much louder. Getting hit by a 235 decibel sound ping will likely burst your lungs and cause your brain to hemorrhage, which in most cases will kill you. But if you're lucky enough to survive, you're probably not going to be in great condition. What about bats? Bats also use sonar and they don't burst lungs or hemorrhage brains. Well, the reason for that is simple. Bats are not submarines. More specifically, bat sound frequencies are in the ultrasonic, ranging from 20 to 200 kHz. Human hearing tops out at 20 kHz. These sounds can reach up to 120 decibels, but since they're ultrasonic, we can't hear them. Scare tactics aside, it's unlikely that a submarine will use its sonar to casually distress a swimmer, as a sonar ping works both ways. It helps you find things, but it also helps things find you. A submarine's biggest advantage is its stealth, and using what is equivalent to a massive beacon is a bit counterproductive to this goal. On top of that, ships aren't really allowed to use sonar within 12 nautical miles of the coastline to avoid damage to marine life, which includes swimmers. If these ships detect marine life of any kind, they have to turn their active sonar down or completely off. So perhaps submarines are not your biggest threat in the ocean.
Okay, that's it for me today. Any question? No? Then we can move on to second lecture read by Jiun Lee.
Yes. 지금 바로 하면 되나요?
예.
네. 음, 음. 어, Hi, I'm Jin Lee, and today's topic is underwater acoustic. And I will tell you about the speed of sound and the sound propagation in the ocean and application. We will see the sounds goes on in the ocean and how do people use it. Yeah. Firstly, as we all know, speed of sound can be determined. To do that, we need to know the medium's elastic properties and its density. In Newton Principia, it's calculated as the square roots of the Burke modulus by density. Burke modulus corresponds to the stiffness in fluid. It means that the speed of sound increases with stiffness and decreases with the density. K means the elastic Burke modulus. Yeah, and we can calculate the speed of sounds depend on the temperature, pressure, and salinity. Here, especially, salinity is the dissolved salt contents of the body of water. Pressure depends on the depth and temperature depends on the location. Several formula to get to speed of sounds are introduced in here. Also, each formula have limits such as the temperature range and salinity range. Mostly salinity is depending on which area are they. So it varies depending on the amount of the solar radiation energy observed. Yeah, and the temperature can be changed in the ocean. We can divide in 3 layers. Depending on the depth. Firstly, at the surface area, temperature does not change at much, so we can call it isothermal layer because wind can mix water up and down. Yeah. Also, due to increase in pressure in a isothermal layer, the speed of sound increase a little bit. And the thermal decline layer has a steep temperature gradient. It can be divided deep water and the upper mixed water. Yeah, yeah. Thermal decline is the middle layer of the isothermal and deep water. And depending on the season, latitude, and intense mixing of the wind, the thermal decline may be a semi-permanent feature of the water, and it may form temporarily during the day and night due to the phenomena such as heating and cooling. Yeah, and this layer, speed of sound, is more affected by temperature. Yeah, so they can get a similar situation. And lastly, in deep ocean, the deeper the depth, the speed of sound is more affected by pressure, and pressure is higher the deeper, so the speed of sounds it goes higher. Yeah. Moreover, depth of each layer depends on location. Such as, for instance, at polar region, there is no surface layer and decline, and the equator there is no wind, so surface layer is so shallow. Yeah. And at region 3 and 2 and 3, thermocline and deep ocean, as main thermocline decrease and the deep layer increase in the region, so sounds channel generate. Here's low frequency wave can travel 1,000 kilometers, and we call it deep sounds channel. Shallow zone can be created at the border of TSC. Reflection. Reflection is the change of the direction of the waves as they move between the material with different property. Yeah. When a wave encounter at the medium, which has different propagation velocity, so wave direction can be changed. And it happens also in water. Sound is also kind of wave, so refraction can occur. The angle changed by refraction is well known by Snell's law. Yeah. The larger the speed difference, the more bending. So the more closer the vertical direction of the plane of the medium. Yeah. The change in the speed of sound with the depth causes important characteristic due to refraction. Sound waves are not propagated in the straight line, but rather curves. Yeah. Secondly, here are some application system of sound wave in the sea. We will see the 5 things. First one is the active echo raining sonar. Yeah. Secondly, the sound wave is also can be needed to communicate in underwater to other sensor monitoring center and satellite. With acoustic, there is a very high refraction in deep ocean underwater. So therefore, this technology is very important. Yeah. Third thing is about the acoustic positioning, and let's see the video about that. Oh, can you guys see this video?
Yes.
감사합니다.
사운드가 안 들리는데 그 옵션 체크를 안 하신 모양이죠. 사운드 옵션. 공유 중지를 하시고 다시 공유하기 다시 눌러갖고 들어오면서 왼쪽 밑에 코너에 사운드 공유 세션을 누르세요. 화면 공유를 중지하시라고. 화면
네.
공유 중지.
공유 중지.
다시 공유하면서 왼쪽 밑에 사운드 옵션이 있어.
사운드,
At ranges of up to 1,000
들리시나요?
네.
meters. Subsonus can track other Subsonus USBLs, and also Subsonus tags, a battery-powered acoustic transponder. The Subsonus kit includes everything you need to get started: a subsea cable to provide both power and data to the transducer, a Subsonus transducer with a vertical connector designed for easy pole mounting on a vessel, a power over Ethernet injector, and a pole mount bracket. If you require a transponder, the Subsonus tag kit contains a tracking device. Subsonus requires an absolute positioning and timing source. In this case, we're using an advanced navigation GNSS compass. However, other similar systems can be used. Take the Subsonus with the vertical connector. Connect the subsea cable to it and attach it to an over-the-side pole using the mounting bracket. When in use, the transducer should be below the vessel keel and away from sources of noise or cavitation, such as propellers or jets. The pole should be mounted as rigidly as possible. The maximum recommended speed of the vessel while the unit is deployed is 5 knots. A retractable pole is recommended to allow for high-speed transits to and from a worksite. To install Subsonus on an ROV or other subsea vehicle, it is recommended to use a Subsonus unit with a horizontal connector. Mount the Subsonus transducer to the top of the vehicle for best acoustic performance. With the forward arrow aligned with the forward direction of the vehicle. Ensure the unit is well clear of thrusters or sources of noise. A connecting cable, such as a whip, can be used to provide power and data via Ethernet through the subsea vehicle system. To track assets such as divers or subsea infrastructure, Subsonus tag acoustic positioning transponders are recommended as a simple, cost-effective solution. Ensure the Subsonus tag is fully charged before being deployed. For optimal performance, make sure the device is placed with the blue transducer pointing towards the surface or tracking Subsonus and away from propellers or thrusters. You can now simultaneously track hundreds of underwater assets without the need for industrial computers, external sound velocity sensors, or additional inertial navigation systems. Subsonus by Advanced Navigation. For more information and a free trial request, visit Advanced.
Oh, yeah. Yeah, that's also kind of the application system of the speed of sound. Third thing is also using several sensors such as Doppler effect sensor and scanning sonar. We can find the direction to go in the deep ocean. Yeah. And lastly, acoustic stabilization devices are used to gain real-time data necessary to respond to criminal activity and emergency situation. These devices are used by law enforcement personnel to assess threats. Yeah. And it can evaluate incident and make appropriate decisions. Yeah, that's all thing I prepared, and thank you for listening.
Any question to Jiun? No question? And we can move on to discussion session needed by Ballet.
Yes, hello, can you hear me?
Yes. Go ahead.
Okay, so let's start off this discussion session by a small Kahoot game to test your skills in underwater acoustics. Okay, we'll wait a little bit longer. Okay, so let's start. I think we have enough players. Oh, okay.
Valer, because the number of participants is small, can you write down the number, Kahoot number at the chatting box so that later they can participate?
Okay. Okay, good. So yeah, speed of sound is 1,500 meters per second. And I'll share the Kahoot game at the end along with the slides I have prepared. So yeah, we've seen that there exist equations in order to determine the speed of sound and on function of temperature, salinity, and pressure, but there was nothing about conductivity. When was the first successful measurement of the speed of sound in water? Okay, so it was in fact the 19th century. It was an experiment led by two scientists, a mathematician and a physicist, in 1826 on Lake Geneva, and they rang a bell underwater and ignited gunpowder on the boat. And a second boat a few kilometers away was observed the bell sound and the gunpowder flash, and their calculations led to the first accurate speed measurement of sound. True or false? Marine mammals use echolocation, which is a form of active sonar, to navigate and find prey underwater. Good. So echolocation is used by bats, but also by marine mammals, such as dolphins and whales. And they use it to avoid obstacles, to find prey, and also for social interactions. And changes in rate, pitch, and or structure of sounds communicate different messages. What is the primary application of underwater acoustics in oceanography and marine biology? So the field here was underwater acoustics for oceanography and marine biology is actually studying marine life and behavior. I see that many of you use the mapping the seafloor, but it's actually comes after. True or false? Underwater acoustic communication is limited to a short distances due to high absorption of sound in water. So we've seen that the deep sound channel is a place where the sound waves are channeled, and it allows sound to travel thousands of miles in the ocean without losing too much energy. And hydrophones can pick up well sounds and minimum noises from many kilometers away. So it's actually the preferred method of measuring in the ocean. What is a spectrogram? Okay. So yeah, it's a visual representation of the spectrum of frequencies of a signal over time. It's used for marine wildlife observations, such as you can see on this picture. By analyzing spectrograms, we can find out what animals are present. So they can help identify marine life, study geological activity, but also monitor human-made noise, such as propellers, ship propellers, or submarine propellers. And analyzing them gives us insights on ocean ecosystem and assesses our impact on marine life. Yep, sound navigation and ranging. So which type of sonar is used to create detailed images of the seafloor and detect submerged objects like shipwrecks? Passive or active? So it's active. You send a ping and you receive the sent message back. Which type of sonar is used by marine biologists to study the behavior of marine mammals? Active or passive? Yeah, because this time it's passive. So which is the main factor that influences the speed of sound in water? We've seen that in Jun Lee's presentation. It is temperature. The temperature gradient, the speed of sound gradient in respect to temperature is the highest in the ocean. It's a 4.5 meters difference per 1 Celsius increase in temperature. So thank you for playing. We'll pass on to the slides in a moment. And Luan, once again, who wins? Well played. Okay. So I'll send the Kahoot link for you guys to see it again.
The prize to him?
Excuse me?
Any sweet prize to first runner?
Oh, no, I don't have any. Sorry.
Okay, very nice to have a coat again.
Okay, so now some questions for guests to answer.
Oh, you have more. All right, go ahead.
Oh yes, I have more. Yes. So sources of underwater sound. Can you think of any sources of underwater sound? Currents? Yeah. Earthquakes, marine life. Is that all? Okay. Ships. So this is what I propose. So there's marine life. So you guys thought of that. There's also earthquakes, as Pierre mentioned. These are basically geological activities and underwater from the underwater seabed. There's also human activities, so ships, submarines, offshore drilling also makes a lot of noise. Construction and sonar, active sonar. But there are also the waves and the wind, which creates a lot of ambient noise. And underwater technologies, such as instruments that are in the sea, and a bit more, such as gas bubble emissions from the seabed, also can sometimes happen. So what do you think are the similarities in air and water for sound propagation? Any ideas? It is fast. So is that a similarity or a difference? So water is a okay. Wave properties and Snell's law. Any other differences? No. So there are actually a bit more differences than just the speed. There's also the propagation distance. So sound travels farther in water. And also water is incompressible while air is compressible. And the speed variability is higher in the water. And the sound waves are actually bended due to Snell's law much more easily in water because of the temperature and salinity and pressure gradient in water. So most of the time, water does not propagate in a straight direction in water, unlike in air. And of course, so we have the nature of waves, which are similar, and the physical laws. And also frequency dependent. So sound attenuation is a frequency dependent in both air and water, even though they attenuate at different rates. So we've seen that water travels much farther in the ocean. And why do you think is sound important for marine life? What do marine animals use sound for? And why do they need it? Tracking their prey, communicating. Okay. Any other important aspects to see? Yeah, to see danger, to perceive their surroundings, navigate, and avoid danger. That's interesting. So yeah, there's communication is a big part of a marine animal. Um, uh, because they use sound to communicate and share information between each other. And they also use echolocation, so that, like we have seen, it aids them in navigation and locating their prey and avoiding predators. But also breeding, because they use it for courtship and attracting mates. So this is a form of communication, of course. But they also use it for perceiving their surroundings with environmental clues, such as wave and sound to help them navigate. And one big thing is human-generated underwater noises can disrupt marine life, affecting their behavior and well-being. And so here, what do you think? What precautions would you take to avoid this problem? Because ambient noise it's the noise referred to as underwater noise pollution, generated by human sound in aquatic environments. So the question is, what precautions would you take to avoid this problem? Because marine life highly depends on sound for many parts of their life. We need to, okay. So reduce the sound impact of ship motors. That's a good idea. But it's not the only source of sound. Think of the sources of sound we mentioned earlier. Okay. So reduce the sound footprint of sea plants. Oil extraction. And in terms of regulations, do you think we could put some in place? So we could have a regulatory frameworks to enforce noise restrictions in sensitive areas. So we have quiet ship designs. We could try to promote noise reducing ship technologies, or even use noise reduction measures in underwater construction or in seaplants, as Pierre mentioned. But we could also raise awareness and educate on noise pollution's impact, and most importantly, international collaboration to maybe put to designate quiet marine zones in order for sea life to evolve in a healthier environment. And finally, what are the potential applications of underwater acoustics you can think of? And we'll end on this note. Anyone? Okay. So we can use it for underwater archaeology, environmental monitoring, marine healthcare, defense and security. Detect damage. Damage to wildlife or to ships? What type of damage? Okay. Well, thank you for participating. And this is the end of my discussion.
Thank you for leading the nice discussion. All right, this is the end of this class. Any other question? Schedule or other items? No.
I'll put the Zoom link at the end of my presentation. Kahoot link.
Can you upload the
Yes.
file later?
Mm.
Thank you. All right, then see you next week at the class this time. Next week I will be in Daejeon. So see you there. Bye now.
Bye.